you a question?
Yes.
If we can run several gradient descent on the policy gradient, if it were, I do the experiment, I think it's done
Sorry, if you do what?
But to run several gradient descent on the same data.
On the same data?
Yeah.
So that's actually related to what we'll talk about today. So maybe if you hang on until after lecture, I'll explain that a little bit. All right, let's get started. So today's lecture will be on advanced policy gradients, but before we get to that, a few logistical notes. So homework 2 is due today at midnight, so hopefully all of you are nearly done with that. Please don't be late. As a reminder, we have 5 cumulative late days, so for all assignments altogether. So if your total number of late days is more than that, then of course we can't grade your assignments, so do make sure you get things in on time. Homework 3 will come out today, tonight after the due date. For homework 3, please make sure to start early. So homework 3 is going to be on Q-learning and also actor-critic algorithms. Some of these things take quite a while to run, so we'll have you actually running Q-learning for like Atari games and things like that. But they run faster if you have a GPU machine. Even without a GPU, they'll still run, but it'll take a little while. So make sure that you start early so that you don't end up in the unfortunate situation of writing all of your code, getting everything correct, but then not be able to get the results in time. So that's going to be sort of a realistic example of what deep reinforcement learning research looks like for you if you do that, but much better to do it early so that you don't run into that problem. So please don't be late. Final project proposals. Those are going to be due in 1 week. So please make sure that you formed your group, that you're working on final project proposals. For the final project proposals, we'll actually have you submit them through a CMT website that we made for the class, and we'll have your peers in the class actually provide you with feedback. The feedback doesn't actually affect your grade. Like, if someone tells you that your proposal is not very good, we're not going to mark you down for that, but it's more for your benefit to make sure that you're proposing a project that really is going to attempt to do something new that fits with the theme of the class and so forth. So do make sure to take that seriously. And of course, do make sure you actually do the feedback for your peers. We'll have instructions for that after the due date for how to fill out your feedback. So please do get started on the project proposal. Okay, so today's lecture. Today's lecture is going to be a little bit more mathematically involved than the others that I've had so far. It's going to cover some of the theory underlying policy gradient, and we're going to use that theory to then derive a natural policy gradient algorithm. So about half the lecture will be on understanding policy gradient, and then the other half will be on actually deriving the natural policy gradient. So we'll start off with the question, why does policy gradient actually work? We'll talk about how policy gradient can be interpreted as a type of policy iteration. And by the way, when I say policy gradient here, for the purpose of this lecture, this includes both the regular policy gradient we discussed and the actor-critic algorithms. So we're not going to really worry about where the advantage values come from. We just assume you have some critic, which could be just summing together rewards, or could be a function approximator. We're going to talk about how policy gradient, once you interpret it as policy iteration, can be viewed as a type of constrained optimization problem. And we'll see where the constraint actually comes from and why it needs to be there. And then we'll talk about how that constraint formulation under some approximations actually ends up allowing us to derive the natural policy gradient, which is actually a very practical algorithm that we often use in reality when we want to do policy gradient for larger problems. And then we'll talk about the relationship between natural policy gradient and trust regions, which is going to be kind of apparent since the way we got here is by talking about constrained optimization. Okay, so the goals for today will be to understand the policy iteration view of policy gradient, understand how to analyze the policy gradient. Basically, how do you understand, will the policy gradient actually provide improvement? The analysis is a little bit involved, but I think it sheds a lot of light on how policy gradient actually works. And then we're going to try to understand what natural gradient does and how to use it. Okay, so let's recap the policy gradient stuff since that was a little while ago. So the most basic kind of policy gradient algorithm that we covered in this course is the reinforce algorithm. The reinforce algorithm is very simple. You generate some samples from your policy by running your policy. Then you compute an estimate of the policy gradient by summing together the products of the grad log pi's and the summed rewards. And then you take a gradient ascent step. You basically take your old parameter vector and you add your gradient times some step size. And of course, in reality, you can improve all of these, each of these steps. So, there's a return estimation step, which here just sums together a bunch of rewards, but you could also do something fancier here, like you could use a critic network to actually fit a function approximator to the sum of rewards. So there's a lot you can do to improve this step. You can also improve the gradient step. You could, for example, use a more sophisticated optimizer like Adigrad or Atom or something that adapts the step size dynamically. So all that stuff you can do over here. So there are many ways to improve this algorithm. And we also talked about baselines, variance reduction, and so forth. But the most basic kind of heart of this algorithm is that it's going to be computing these products of grad log pi's times some kind of reward to go estimate. And different ways to get that reward to go estimate. We're not actually going to worry about where you get this thing. We're going to mainly worry about what this whole thing is actually doing. So you can use a function approximator there and so on. Okay, so the first question we'll be concerned with is, why does policy gradient actually work? And there's a simple and maybe not entirely satisfying answer. Well, maybe policy gradient just works because it's a gradient. So when you climb a gradient, you get to a better value. That kind of makes sense. We all know about gradient descent and gradient ascent. But maybe there's a deeper reason. Maybe there's something a little more involved going on here. So one of the ways that you can view this algorithm when you represent it kind of graphically like this is that there's basically, other than the sampling, there's two computational steps. You're estimating something about your policy, and I've actually intentionally replaced Q with A here. If you remember, you can use the advantage instead of the Q function, and it's the same thing because it doesn't depend on the value here that you subtract doesn't depend on the action, and using the advantage turns out to make some analysis a lot easier. So let's just say it's, instead of reward to go, it's reward to go minus current value, which is the advantage. So then you can say you have one step, which is estimate the advantage. Estimate the advantage of what? Well, estimate the advantage of the current policy, the one you just generated samples from. That's what you do when you train a critic. That's what you do when you sum together rewards. So step one, estimate the advantage. And then step two, use this advantage, and this is the advantage of pi, a pi, to get an improved policy pi prime. And that's kind of what you do over here, right? So you've estimated your advantages. Those advantages tell you how much better are some actions than other actions in particular states if you then follow your old policy. And then you're going to use those advantage estimates to get a new policy pi prime that is better than your previous one. And the way that you get pi prime is by taking one gradient step. So now viewed in this way, this maybe looks a little bit familiar to some of you. This maybe looks a bit like those things we discussed when we talked about policy gradient, when we talked about actor critic, specifically when we discussed policy iteration. Because policy iteration, if you recall, has very similar looking two steps. Evaluate the advantage, and then set the policy to be a better policy. So if you kind of separate it out into an advantage evaluation and this policy improvement using the estimated advantage, it looks a lot like a policy iteration algorithm. So this is more of an aesthetic argument than a formal argument. This is just saying, well, if I write it down in this way, it looks an awful lot like the policy iteration. But I can actually make this a little bit more formal. So what I'm going to do next is I'm going to show that you can use the advantage of the previous policy to get a better policy, and that the resulting method looks like policy gradient. So I'm going to show you how you can interpret policy gradient as policy iteration. So first, we have to actually write down what it is that we're going to try to optimize when we're trying to get our better policy pi prime. And what I think we should optimize is we should optimize the difference in the returns. So let's say theta prime is going to be the parameters of our new policy. Theta is the parameter of our old policy. So we're trying to find theta prime. And what I'm going to say that we'd like to do is we're going to maximize j of theta prime minus j of theta. So that's how much better is your new policy than your old one. It's a very reasonable thing to do. You want to improve your policy, make it better than the old one by as much as possible. That's going to be our goal. And just as a reminder, j theta, this is just the objective of reinforcement learning. It's the expectation of the reward under the trajectory distribution for theta. And j of theta prime is the expectation of the reward under the trajectory distribution for theta prime. Okay, so that's our objective. We want j theta prime minus j theta to be big. And of course, in order to make it big, we first need to know what it is. So my claim, and the claim that I'm going to show on this slide, is that j theta prime minus j theta is equal to the expectation under theta prime, so the expectation under this new thing that you're computing, of the advantage of theta, the advantage of the old policy. What does this mean? This means that if you find a new policy that maximizes the under expectation the advantage of the states and actions that this new policy takes, but with respect to the advantage of the old policy, then maximizing that is exactly equivalent to maximizing the improvement over the old policy. This is a bit of a non-trivial statement because remember that A pi theta is telling you how much better is the action AT than any other action in state ST if you then follow the policy pi theta. We're not actually going to follow the policy pi theta, we're going to follow the policy pi theta prime. But what I'm claiming here is that if you do this in expectation for all time steps for all states and actions, if you maximize this quantity, then you are in fact maximizing the difference between the returns of the two policies. So it's not entirely trivial because A pi theta is the advantage of the old policy, not the new one. Okay, so let's go through this derivation. So first what I'm going to do, I'm going to leave this first term j theta prime alone, but I'm going to replace the second term by the expectation of the value function of the old policy, pi theta, with respect to the initial state distribution. So remember that the value function is actually defined as the expected reward if you start in a particular state. So if you take the value function in the initial state and you average it over all possible initial states, that gives you exactly the reinforcement learning objective. So I can substitute this in without any trouble. And now what I'm going to do is I'm going to change the distribution under which I take this expectation. So instead of taking this expectation with respect to S0, sorry, this should be P of S0, S0 distributed according to P of S0, I'm going to change it to be an expectation under a trajectory distribution. It's totally fine to do this because the stuff inside the expectation only depends on the initial state. And the initial state distribution is the same for all policies. So I can, without introducing any trouble, I can change this distribution to be a distribution over trajectories for any trajectory distribution for any policy, provided its initial state distribution is the same. So all policies will have the same initial state distribution, so I can put in p theta prime of tau in here. I could also put in p theta of tau or p any policy of tau, right? So any choice here is fine, and I'm going to choose to put in p theta prime of tau. Okay, so I haven't really changed anything, I'm just manipulating a little bit of algebra so far. And now I'm going to do something a little bit strange. Now that I have this expectation under p theta prime of tau, I'll actually put in this telescoping sum. So I'm going to replace this v pi theta of S0 with a sum over all time steps from 0 to infinity, or whatever my horizon is. So if my horizon is less than infinity, you put in capital T there, of gamma to the t, the discount to the t, times the value at that time step, minus the same sum from 1 to infinity. Now, this is exactly equal to what I had up here because this is just a telescoping sum. So basically, if you, let's see, is there a marker here? There is a marker. Okay, so it's a telescoping sum because that first part, the one that sums from 0 to infinity, it has like V0. Can everyone see this? Raise your hand if you cannot see it. Okay, someone in the back can't see it. Let me get a brighter marker. Okay, so the first sum, it has V0 plus V1. Raise your hand if you can't see it. Okay, good, everyone's good. Plus V1, plus V2, etc. And actually there's like a gamma here, so it's gamma, gamma squared, etc. The second term, the one that's subtracting from 1 to infinity, it's going to have minus gamma V1, minus gamma V2, etc., etc., etc. At the end, there's going to be a little dangling thingy if that infinity is actually a capital T. One of them will go off the end. But we don't care because gamma to a huge number is going to go to 0 anyway. So the tail end of this thing doesn't matter. It's only the beginning that matters. So now, because you're subtracting these and adding these cancel, and all you're left with is the V0. So there's a telescoping sum. So it's totally OK to substitute that thing. Does anyone disagree that it's OK? Raise your hand if you have an issue with that. Everyone's good? All right, so telescoping sum. Now, we're going to do a little bit of algebra on this. We're going to collect some terms. You see they both have a gamma to the t multiplier in front of them. So you can say that this one here, this is actually can also be a sum from 0 to infinity if you add a t plus 1 here and if you put a t plus 1 here, right? That's just change of variables, so you can make them both be sums from 0, put in the t plus 1, and it has an extra gamma term in front. So you can collect the terms and express it like this. Good. Now the first term, j of theta prime, there we'll just substitute it in the definition up here. So j of theta prime is just the expectation, again under p theta prime, of the total rewards. And now you can all kind of guess what we're going to do. Any guesses about what we're going to do? Yeah, we're going to put them together. So expectation under the same thing, so you can take the expectation outside, collect the terms, and you get gamma to the t times r from here, times gamma v pi from here, and then v pi st from here. And now this thing is equal to what? A. Yeah, that's right. So we just substitute in the definition of advantage, and we get this. Now, so far, we haven't made any approximation. This is just all algebra. So this is just showing the difference between j theta prime and j theta is this expected advantage, which is a little surprising. Like, that's saying that all you have to do is, for all the time steps, for all states in expectation, maximize the advantage of the old policy. And if you can do that exactly, you will actually maximize the difference, the improvement from the new policy minus the old one. Of course, j theta isn't changing as you do this, so this is exactly equivalent to just maximizing the value of your new policy. So if you can do this, you can basically solve the RL problem. Yes?
This is not true exactly when you have finite horizon with small t.
So the question was, this isn't true in general if you have finite horizon with small t. If you have finite horizon with small t, you have to take a little bit of care here. You have to put in, I think you have to put in like a capital T minus 1 over here or something like that. So when you have finite horizon with small t, there's a little bit of a detail, there's a little bit of bookkeeping you have to do. And that bookkeeping has to do with how you define trajectories. So let's say that my horizon is 3. Do I define my trajectory as S0, A0, S1, A1, or sorry, A1, S2? Or do I define it as S2 comma A2? So do I have this dangling action at the end or not? If I don't, if my trajectory ends in a state rather than an action, which makes sense because why would you take an action at the end? There's no next state. Then actually everything is fine because this last state will be the state that sort of dangles off the end of this thing and doesn't appear in the other one, so that's okay. Yeah, you just have to be a little careful with bookkeeping at the end of the trajectory. Okay, so that's good. That's good to know. So now let's work with this thing. Let's work with this quantity a little bit. It's a nice relationship that we have, but it's not really making our lives much easier because before we were trying to maximize expected reward under p theta of tau. Now we're trying to maximize expected advantage under p theta of tau, but we still have this expectation over p theta tau on the outside. So in some ways, we haven't really made our life any easier. So what we can do is we can massage this thing and actually get back something that's going to look an awful lot like policy gradient. So we have an advantage under pi theta, expectation under pi theta prime. And what we'd really like to do is we'd like to change this so that the expectations are under pi theta. Because if the expectations are all under pi theta, then we don't have to generate any more experience. We can just do maximization on that objective computationally without needing to take more samples. Unfortunately, right now the expectation is under pi theta prime, which is hard because that's what we're changing. Right, so the question was, can we use importance sampling? The answer is yes, we can. So that's what we're going to do next. First, we're going to rewrite this thing a little bit. We're going to take the sum outside of the expectation. And this is what we saw before when we talked about the RL objective. If we take the sum outside of the expectation, we can write this as a sum of expectations under the state marginals. So at every time step, take the expectation under p theta prime of st. And inside of that, we have an expectation over the corresponding action distribution, AT distributed according to pi theta prime of AT given ST. And then inside of that, we have the advantage. So now, for those of you that remember the policy gradient lecture from earlier, at the end of the policy gradient lecture, we talked about how if you have an expectation under some distribution, and you would really like to have an expectation under a different distribution, what you can do is you can use importance sampling. So if you have an expectation under P, and you really, really want an expectation under Q, just take the expectation under Q, but multiply your function value by P over X divided by Q over X. So this is just importance sampling. So now, what we're going to do is we're going to plug in importance sampling for this inner expectation only. So now we're going to change this to be pi theta AT given ST, and on the side we have this importance weight ratio, pi theta prime divided by pi theta. As we discussed in the policy gradient lecture, we could do importance sampling for the whole trajectory, but that's quite undesirable because then you have a product of many of these pi thetas, and a product of many, many probabilities tends to be quite degenerate. So if you have, let's say, discrete actions, all these probabilities are, at the top, for example, are going to be less than 1. You multiply a lot of numbers that are less than 1, you get a number that's very close to 0. Or put another way, the importance weights become exponentially degenerate as your time horizon gets longer. But here we don't yet have that problem. We just have the importance weight at a single time step. Of course, we haven't completely gotten rid of expectations under pi theta prime because we still have the state distribution out here. So this is a well-behaved objective. It's just not quite the objective that we want because we still have the expectation out here, and computing the derivative with respect to the state marginal, of course, requires us to generate samples, which is what we've been trying to avoid. So, is it okay to just use p theta of st here instead of p theta prime of st? That's kind of what we'd really like to do. If we just get rid of that little tiny prime symbol, it's such a small symbol that maybe no one will notice, then everything is fine. Then you just generate samples from pi theta, and then you optimize this thing, and that's a fairly easy thing to do. So is it okay to ignore that little prime symbol? While it's a simple question, unfortunately it has a somewhat complicated answer that's going to occupy maybe like a quarter of today's lecture. So is it okay to ignore the distribution mismatch? And that's what we're going to analyze now. Is it okay to get rid of that little annoying prime symbol? So what we'd like to do is we'd like to somehow say that the expectation of this whole thing under p theta prime is close or approximately equal to its expectation under p theta. So if we just get rid of that prime, then the only place where theta prime still appears is up here. So maximizing that with respect to theta prime is actually pretty straightforward. You just have a bunch of terms, a bunch of samples from pi theta that aren't going to change, and then in here you have something that multiplies it that depends on theta prime. So if we can get things into this form, maximizing this expression is actually pretty straightforward. So can we do that? Can we just switch the prime in the theta prime to theta? So why do we want this to be true? Well, we want it to be true because if it's true, then this thing, I'm going to call it a bar theta prime, just so that I don't have to write out this massive monstrosity every time. If this is true, then we can just grab this a bar theta prime, and we have j theta prime minus j theta is approximately equal to a bar theta prime, which means that we can find our theta prime this should be a theta prime, by taking the argmax of this thing. So taking the argmax of that thing just amounts to running, let's say, gradient ascent on this objective, which we can do without generating any more samples, which is very easy and very desirable. So we'd like to live in a world where it's possible for us to do that. Which is basically that second step in policy iteration. Use your estimated advantages to improve your policy. So is this true, and when is it true? Well, my claim is going to be that p theta of st is close to p theta prime of st when pi theta is close to pi theta prime. Question?
Can we use here the epsilon t from...
Yeah, so the question is, can we use the epsilon t? The answer is yes, we can. And we'll see on the previous slide how we can use the epsilon t. For those of you that don't remember what the epsilon t is, hang on for the next slide. So this is it's kind of an obvious statement, actually, if you think about it. It's like saying, well, if you have two policies and they're similar, they're going to visit similar states. It's kind of almost like an obvious thing. If their two policies are the same, then they'll visit the same states. So it's an obvious statement, but it is a statement that we do have to take some care to prove. And in particular, we don't just want to say that they're close. We want to say, well, they're close in what sense? Are they close in some way that can actually be bounded meaningfully? And maybe it's a little bit less obvious than you might think, because, well, maybe a tiny difference in the policies might cause one of them to like fall off a cliff while the other one doesn't. You know, sometimes the difference between success and failure is razor thin. So is it actually true that this is the case? That's what we're going to try to understand. So first, we need to, of course, define what close means. There is an actual definition that's a little more involved, but I'm going to actually start with a simplified definition, which is going to sort of harken back to something we saw earlier with some epsilons and t's back when we talked about imitation learning. So the simple case I'll start with is, well, what if pi theta, the old policy, is deterministic? It's really not, it's stochastic. But let's analyze the case where it's deterministic, because that's going to be really easy, and then we'll go to the case where it's stochastic. So if pi theta is deterministic, meaning it's just a function that gives you an action in every state, then we can define close as following. We can say that pi theta prime, which is a stochastic policy, is close to pi theta if the probability that pi theta prime takes an action that's not the same as pi theta is bounded by epsilon. It's a very natural way to define what it means for pi theta prime to be close. It's saying it has a probability less than or equal to epsilon of doing something different from theta in all states. So if you define this probability of making a mistake, this is going to look an awful lot like that imitation learning stuff we talked about in the very beginning of the course. So if you remember when we talked about imitation learning, we said, well, if the probability that your imitator makes a mistake is bounded by epsilon, then you can do this derivation that shows how the corresponding state distributions will differ, which you can use to bound the loss of the imitator, if you remember the tightrope walker and so on. So we can do exactly the same thing here. We can say, well, if you're in time step t, the probability of being in some state under theta prime at time step t, we can express as a sum of two terms. The first term says, what if you didn't make any mistakes? What if you perfectly matched pi theta all the way until time step t? And then the second term says, what if you made at least one mistake? So your probability of perfectly matching pi theta until time step t is the probability of perfectly matching it on the first step, times the probability of matching it on the second step, the third, the fourth, and so on. Every step you have an epsilon probability of making a mistake, which means you have a 1 minus epsilon probability of not making a mistake. So the probability that you did not make mistakes for t steps in a row is 1 minus epsilon to the power t, which is what we have here. So that's the probability that you just match the policy perfectly, which means you'll have the same exact state distribution. And with 1 minus that, you have some other state distribution. We don't know what it is, but we call it p mistake because this is the state distribution you get if you make one or more mistakes, where a mistake means you didn't match pi theta. So that's something. You know, this term we kind of don't know anything about, but this term looks really easy. So now, okay, the probability we didn't make a mistake and then some other distribution. So if this seems familiar, it's because this is exactly the analysis that we had with the tightrope walker from before. And just like before, what we're going to analyze is the total variation divergence between p theta prime and p theta. So total variation divergence, I think there was maybe a little confusion last time as to what it means. I write it, you know, like this with the absolute value sign, but just to be totally clear, when I write p of x minus q of x, what that really means is it's the sum over all x of the absolute value of the difference. So this is total variation divergence, meaning the sum of the absolute values of the differences of the probabilities of the distribution over all inputs. So that's what I have here. And of course, because if you substitute in for p theta, for p pi theta prime, this equation, then the first term cancels out because, you know, p theta minus p theta is 0. So all you really are left with is this mistake thing. So you have 1 minus epsilon to the t, which is the weight on this, times the total variation divergence between p mistake and p theta, because the divergence between p theta and p theta is, of course, 0. So that's very convenient. We have just this thing. This number might not be so large, and we'll see that in a second. So we don't really want to assume anything about p mistake. So we'll just say that this part can be as big as any total divergence can possibly be. And the largest possible total variation divergence is 2, because if one of the distributions is 1.0 in one state and the other is 1.0 in another state, you get 1 plus 1, which is 2. So this thing is less than or equal to 2 times this stuff. And then if you remember the tightrope walker derivation, we said that, well, there's this useful identity. We don't want to deal with exponentials in t, but 1 minus epsilon to the t is greater than or equal to 1 minus epsilon times t for epsilon is 0 to 1. So we can bound this in a much simpler way just by saying it's less than or equal to 2 times epsilon times t. So that's the bound on the total variation divergence between the state marginals at time step t if pi theta prime is a deterministic policy. So it's not a great bound because this, it becomes looser and looser the further you get forward in time, but it's a bound. And if you choose a small enough epsilon, you can make this bound arbitrarily small.
You don't really get to choose that, but you can't know how epsilon varies.
So the question is, you don't get to choose epsilon. Actually, you do. So if you set, for example, theta prime to be equal to theta, then epsilon is 0. And actually, figuring out how to choose epsilon is something that we're going to discuss in detail in the second half of today's lecture. Yeah. But that's a very important point, is that you do have to actually enforce some epsilon. All right. So now let's look at the more general case. So of course, in reality, if pi theta was deterministic, then you're sort of in some weird place where you suddenly have stochastic policies turning into deterministic policies and vice versa, which doesn't really make sense. So let's talk about the case where pi theta was stochastic. Now, if pi theta was stochastic, it turns out that pretty much the same proof still works, but we need to introduce a little bit of additional machinery. So of course, we need a different definition for what it means for the two policies to be close together. So we're going to have pi theta is now an arbitrary distribution, and we're going to say that pi theta prime is close to pi theta if the total variation divergence between these distributions is bounded by epsilon for all states. So the policy is a conditional distribution over actions, so this is now total variation divergence between action distributions. So we have to say this needs to be true at all states. Now, is it really that simple? Well, it turns out that if we have this bound, we can actually still bound the probability that pi theta prime makes a mistake. And you can say, well, what does it mean to make a mistake when a mistake is trying to match a stochastic policy? The intuition here is the following. Let's say that you implement this in a computer. In a computer, you don't have true random numbers, you have pseudo-random numbers. They're generated from a seed. So if you take the same random seed twice and run the same stochastic policies, you get exactly the same actions. So the intuition behind the idea of making a mistake here is that if you were to use the same random seed twice and run pi theta versus run pi theta prime, what's the probability that they'll agree for the same random seed? And it turns out that that probability is also bounded by epsilon. Now, of course, random seeds are something that computer scientists invented. If you want to look at this more from the standpoint of probability, you need a bunch of theorems and lemmas, and we've got those too. So a useful lemma, which is what we're going to use to actually connect this to the stuff on the previous slide, is the following. Now, this lemma is a little bit technical. It's not actually that complicated, but for those of you, like if you guys get confused on this, just remember the random seed thing, because that's saying exactly the same thing. But just to walk you through this lemma, you have some random variable x, and you have two distributions, px and py. And I'm going to call this p subscript x and p subscript y. If the total variation divergence between p subscript x and p subscript y is equal to epsilon, then there exists some other joint distribution over two variables x and y, such that the marginals of this joint, for x the marginal is px, and for y the marginal is py, and the probability that the probability that x is equal to y is epsilon. So if I have one of my distributions outputting x, the other is outputting y, they have some joint distribution, and the probability they'll output the same thing is equal to epsilon if their total variation divergence, when I apply them to the same variable, is equal to epsilon. Which is just a fancy way of saying if I use the same random seed for both, they'll agree with probability epsilon. So px of x agrees with py of y with probability epsilon. So of course, if you bound this by epsilon, then this probability is also bounded by epsilon. So that means that if you apply this lemma then to the policies, you say that pi theta prime takes a different actions than pi theta with probability at most epsilon. All right, so now we're bounding the probability of a mistake, which means that we can again express the difference, the total variation divergence between p theta prime st and p theta st as just the sum of two terms, where the first one is the probability that you didn't make a mistake, which is 1 minus epsilon to the t, and the second is the probability of the mistake, which is 1 minus epsilon to the t, and substitute that in and get this relationship. So this part is exactly the same as before. It's bounded by 2 times epsilon t, and the way that we got there is by using this derivation that says, well, if you keep the random seed fixed, they'll make different actions with probability at most epsilon. So that's the stochastic case. Okay, does anyone have any questions about these state distribution bounds? So this bit is it's a bit involved, but it's important to go through this derivation because these kind of state distribution bounds crop up again and again when we analyze reinforcement learning algorithms, because reinforcement learning algorithms act in sequential decision processes, and very often we have to relate differences in policies to differences in state distributions. Now, of course, what we really want is we want to understand the objective, not just the state distribution. So this tells us that if our policies are close, and now we define what close means, then our state distributions are close, and we define what that means also. So now is it okay to drop that theta prime and replace it with theta? Well, we do need to understand what that's going to do to our objective. This analysis also is very, very similar to the analysis of the loss in the tightrope walker example. So I'm going to write it out here for some generic score function f of st, and then we'll just substitute the advantage in there. So if you have the expectation under some state distribution p theta prime of some function f of st, then that's, of course, equal by the definition of the expectation to just the sum of the products of the probabilities and the function. That's just the definition of expectation. And then I can bound this by the expectation under a different distribution p theta minus the total variation divergence between them times the maximum value that f can take, assuming f is always positive. So if f is always positive, then this is true. So that's like saying that basically every time you vary, every time you move away from p theta prime, like the worst possible thing happens. The worst possible thing in this case is your objective value is lowered by the maximum of f of st. So it's saying, okay, you either match p theta st perfectly, or the worst thing in the world happens. So that's a bound. And now, of course, this is just an expectation, so I can rewrite it as an expectation. And here I can plug in my bound for the total variation divergence. So I say that, well, the expectation under p theta prime of st of some positive function f of st is greater than or equal to the expectation under p theta minus 2 times epsilon times t times the worst possible thing that can happen. And of course, if we can make epsilon small enough, then that second term can become negligible. So now we want to plug in, for f of st, we want to plug in this thing here, this complicated thing. So that means that the quantity that we really want, so this is the one under theta prime, this is the correct objective. This objective is greater than or equal to the simplified objective where you put in theta instead of theta prime, but you pay a little cost for your approximation, which is 2 times epsilon times t times some constant. And the constant is on the order of capital T times R max. R max is the largest reward you can possibly get. Or if you have a discount, basically if capital T goes to infinity, but you have a discount, then it's on the order of R max divided by 1 minus gamma, because 1 over 1 minus gamma is sort of the effective discount. So if you look at the geometric series, you have gamma to the first power, second power, third power, et cetera, et cetera, et cetera. You add all those together, that becomes 1 over 1 minus gamma. So if you have an infinite horizon, but you have a gamma less than 1, then this is the order that you have. There should be a gamma here too. There should be a gamma to the t. So now let's try to understand this a little bit more. This second term, this is basically how much suboptimality you incur. It's not a nice term. It has some pretty big numbers in there. So it's all multiplied by epsilon in the front. So if you make epsilon small enough, you're in good shape. But you have like a t here and you have a t here because your advantages are on the order t. So the order of this term is quadratic in your horizon. So it's either quadratic in capital T if you have a finite horizon, or it's quadratic in 1 over 1 minus gamma if you have a discount, which is kind of nasty. Like that means that the longer the effective horizon of your problem is, you're going to pay a quadratic price in suboptimality, which means that in order to improve your policy, you're going to need to take quadratically smaller steps. You're going to need to decrease epsilon to compensate for that. So it is a bound It's not a really great bound, and it's a pretty loose bound in practice, but it gives us something to work with so that we can actually derive some practically useful algorithms. Okay. Does anyone have any questions about this?
Can you say again why C is related to capital T?
Okay. So the question was, why does C relate to the horizon? Well, C is basically taking care of the function value, which is this thing, and it's saying, what's the largest value that this thing could take on? Now, this thing has an advantage inside of it. And the advantage is the expected sum of future rewards minus the current value. So maybe you got unlucky. You're in a state where the value is like 0, but the future rewards are huge. So in general, if you want to bound all this stuff, you might be paying as much, like the maximum price that you might pay is the largest reward times the number of steps of the future, which is on the order of t. So that's why you have an R max and a t. Or if you have an infinite horizon discount, R max divided by 1 minus gamma.
Why you don't multiply it with t again? Like t divided by 1.
So the question is, why don't I multiply what by t?
Like instead of R max divided by 1 minus gamma, like the same thing multiplied by t.
Oh, okay. So let me walk through this a little bit. So let's say that you pay a price of R max every step, right? So you say, I'm going to pay R max on the first time step, I'm going to pay R max on the second time step, and on the third, and so on. But if you have a discount, then it's R max, gamma R max, plus gamma squared R max, and so on, right? So now you can take the R max out, so it's R max times the sum over t of gamma to the t. And this part is 1 over 1 minus gamma. So as a general rule in analysis of reinforcement learning algorithms, if you ever see 1 over 1 minus gamma, just mentally substitute horizon. Like 1 over 1 minus gamma means horizon. All right. So we can maximize this thing, and that kind of maximize the bound on the thing that we want. So that's what we're going to do. We're not quite done yet. There's a little appendix I want to add to this, which is that total variation divergence is kind of a massive pain to deal with. For practical distributions, calculating total variation divergence, approximating it, and so on, it's kind of annoying. And we would rather not deal with total variation divergence. So there's actually a much more convenient bound. So the one that we had before was, p theta is close to p theta prime if the total variation divergence between the pi's is bounded. But a more convenient bound is going to make use of a relationship between total variation divergence and KL divergence. This is just always true for total variation divergence and KL divergence. So the total variation divergence between two distributions is less than or equal to the square root of 1/2 of the KL divergence between those distributions. What is KL divergence? Well, KL divergence is defined by this thing. It's the expectation under the first distribution of the log of the ratio of the other two. Kind of a weird expression. You might say, well, okay, we had this nice thing with absolute value. Now we stuck in this horrible thing with a bunch of logs. Aren't we just making our lives harder? Actually, no. So KL divergence, even though it seems like an ugly thing with a bunch of logs in it, it's actually simpler in many cases because for many distributions, there's a very convenient form for the KL divergence. For example, if you have Gaussian distributions, there's just a formula you can write down for the KL divergence between two Gaussian distributions. You can generalize to continuous variables very readily. For discrete variables, there's a bunch of approximations that you can do to KL divergence that are also very convenient to use. So KL divergence is just a lot easier to work with in many cases than total variation divergence. So it's quite nice that we can bound this thing by the KL divergence, because if we bound this thing by KL divergence and the total variation divergence bounds the state distribution, that means that the whole thing can be bounded by KL divergence on the policies, and that's going to be much easier for us to deal with. So even though all the analysis so far has been in terms of total variation divergence, in reality what we really use is the KL divergence bound, because it makes a lot of the downstream kind of algorithms much easier to deal with. Okay, so now let me kind of bring this all together and say, well, okay, how do you actually use this objective? We've shown that if you just plug in p theta st instead of p theta prime st, this thing is kind of close to the objective you want, provided that the two policies are similar. So what we might be tempted to do is say, well, let's optimize theta prime by taking the argmax of this objective. And this is not a hard thing to do because you just generated some samples a long time ago, and then you have to just compute the gradient of this, and computing the gradient of this is pretty straightforward. The only place where theta prime appears is in here. Automatic differentiation software will do it for you. But this is only a valid objective if you stay close to theta. So it's not enough to just plug this into TensorFlow and let it maximize it. You have to impose a constraint. And the constraint has to be such that the KL divergence between pi theta prime and pi theta is bounded. So if you can find a way to impose this constraint, then you can plug things into your favorite autodiff software and get an improved policy. So for small enough epsilon, this is guaranteed to improve j theta prime minus j theta, which is a thing that you really want. So how do we do that? Well, there are a few ways to do it. And actually, what I'm going to do, I'm going to come back to this later. What I'm going to do is I'm going to take a break now. Yeah, let's, and I'll finish after the break. So let's take a 3-minute break, and then we'll talk about algorithms. So see you back here at 10:57.
So all of these expressions where you have a pi theta, so what if I had started with some pathological initial policy where, like, can't I have started with one where a was 0 for all actions?
Yes. So the whole importance sampling thing, unfortunately, requires you to have the same support. So if the two distributions have like non-overlapping support, then the importance sampling argument breaks down.
Oh, yeah, I guess it means something slightly different, which is like, aren't there policies where the advantage of any action is 0? Like it takes an action, but then.
So in the general case, we're going to assume that let's say no action has non-zero probability, which is a pretty easy condition to impose. And in that case, you can have a really technical argument about signal-to-noise ratios, but the signal is still there. It might be drowned out by noise, and you might need exponentially many samples to see it. But so long as you don't actually have probabilities of 0, it's there.
Okay.
You could have removed, like, decided that pi of p of theta prime equal to p of theta, like previously before you did this double expectations,
Yeah.
and the problem is solved.
Well, yeah. So we will want theta prime to move away from theta a little bit, and we'll discuss if, that kind of comes down to the actual practical algorithms. So what I'll discuss after the break is actually you can do just the original constraint optimization, or you can do like a local linearization at theta prime equals theta, and then optimize essentially the Taylor expansion of this thing. So there are a few different options there. You could actually tackle just the original constraint optimization directly.
I'm just a little confused about the P of S. For here, it do not depend on theta, right? It's a transition of the environment.
So when I say P of S script T,
Yeah.
that's referring to the distribution over states at a particular time step. The distribution over states at the first time step does not depend on the policy. But the distribution on the second step most definitely does.
Oh, so this it also has theta.
Well, no. So the way you obtain state marginals is by marginalizing that distribution. So it's not any term in this distribution. So you have to take the product and then sum out all the rest.
Oh.
So it's a marginal of this thing, whereas these are all conditionals.
Oh, so your PST is a marginal.
Yes.
So it's not the transition.
Yes. Yeah. And this is very important. It has to be a marginal for all this to make
it has
sense.
a theta.
Yeah. Yeah. Okay. I need to resume the lecture. Sorry.
Do you have a corresponding lecture?
Sorry. I really need to resume the lecture. Otherwise, I'm going to run out of time. Okay. So now, in the second half of today's lecture, I'm going to talk about algorithms. So we've derived a little bit of the theory. We see that, okay, if we optimize this surrogate objective with p theta instead of p theta prime in there, we'll actually improve the value of our policy, but we have to stay close to the old policy. So what are some of the ways that we can actually do this in practice? What are some algorithms that we can employ? So one algorithm that we can employ is actually based on something called dual gradient descent, which I won't derive in detail in today's lecture, although it'll come up in more detail later on in the course. But this algorithm is basically going to aim to directly solve this problem. approximately, directly but approximately. So the problem is that you have an objective and you have a constraint. So when you have an objective and you have a constraint, one really convenient thing to do is to write out the Lagrangian. So the Lagrangian is a function of the primal variables, which here are theta prime, and a Lagrange multiplier, which here is lambda. There's this constraint that has a Lagrange multiplier lambda. So you write out the Lagrangian, you have the objective value, it's maximizing. This is a little weird for those of you that are used to seeing convex optimization stuff. Usually in convex optimization you minimize. Here we're maximizing. So there's going to be a little bit of a disconnect as far as the signs. So don't worry about the signs. It's just because it's maximization rather than minimization. But we're maximizing the objective. And then if you have a constraint, now you subtract it because it's maximization. Lambda times the KL divergence minus epsilon. So subtract epsilon, this thing less than or equal to 0, put that in here. So that's the Lagrangian. Now, if you have a problem like this, you have some crazy constraint and some crazy objective, one way that you can optimize this constraint optimization problem is to alternate between optimizing the Lagrangian with respect to the primal variables theta prime and then updating the dual variable lambda. This is called dual gradient descent. I'm not going to derive dual gradient descent here. I will actually derive it later. But for now, I'll ask you to just take this on faith, because otherwise I'm going to run out of time in today's lecture, that this procedure will actually do the job. Mechanically, what this procedure looks like is actually very simple. Step 1, maximize the Lagrangian with respect to theta prime. Just like literally shove this thing into like TensorFlow or something, compute gradients and maximize. It's actually fairly easy to do that because this KL divergence, even though it looks like an ugly thing with a bunch of logs, it's an expectation under this first term of the log of the first term minus the second term. And over here, you have this importance ratio is actually also computing an expectation under the same thing. So it's pretty easy to work the KL divergence in here. I'm not going to derive that, but if you want to do the algebra at home, just write out the definition of KL divergence, plug it in here, and you'll see how it fits. Yes?
Preference for using KL divergence instead of canon for its symmetry?
Yeah, it makes all the derivations way easier to use KL divergence here. You can do constraints with other kinds of divergences. There's quite a bit of research on that, but by far the most popular one is to just directly use KL divergence. And a big part of that is that just like the RL objective, which is an expectation of the reward under some distribution, the KL divergence is also the expectation of something under some distribution. So the punchline for what these things look like when you put them together is that you just have an additional term that you add to the reward, which is the log of the difference of the two things. So that's very convenient because then you don't really even need to modify your code very much. You just change the reward function and it basically just works. But if you want to confirm that, then plug in the definition for this thing and work through the algebra. Okay, so step 1 will be to maximize the Lagrangian with respect to theta prime. And step 2, which we can prove that this is actually the dual of, the gradient of the dual function. The proof for that will be in a later lecture. But step 2 is you basically take your lambda and you increment your lambda by the constraint violation. So you said lambda is now lambda plus alpha times the constraint violation. The intuition behind this is very simple. If the KL divergence is way bigger than it should be, lambda will go up. If the KL divergence is way smaller than it should be, lambda will go down. So you'll adaptively adjust lambda until you actually hit your constraint. There is a somewhat technical result that it can actually be proven that this constraint actually always ends up being tight. So even though it says less than or equal to epsilon, it'll actually come out to be equal to epsilon. It's a little bit more involved to show that, so I'm not going to do that. But it's fine to just say we're going to hit epsilon exactly. So this algorithm, it will enforce the constraint if you run the maximization in step 1 to convergence, if you exactly optimize the Lagrangian, and we'll actually show this in a later lecture. In reality, it'll still actually work even if you do this incompletely. So in practice, for practical kind of deep learning algorithms, of course, you never want to run anything to convergence because you don't know how long convergence will take. So in practice, if we were to actually implement this algorithm, we would run step 1 for some small number of gradient steps, and then we would do step 2. Okay, so this is an actual algorithm that we could use to optimize this objective, and it looks a lot like an importance sampled policy gradient, just where we take the policy gradient for multiple steps. So in practice, what this would look like, collect samples, crunch on this thing for some number of gradient steps, collect more samples, and so on. So it's a version of policy gradient where you can take multiple steps by exploiting importance sampling, and you have to keep track of this term so you don't wander too far away from the policy that you sampled from. Any questions about this method? Okay. So this is kind of the most natural consequence of the theory that I derived, but you can actually get even closer to the standard policy gradient algorithm that we learned about before by making a few additional approximations. Okay, so I'll skip the review to make sure I don't run out of time. And what I'm going to talk about next is actually a different way that you can optimize this objective that ends up looking very, very similar to the policy gradient that we had before. Just again, as a reminder for notation, this thing is kind of a mess. So if you see me write a bar theta prime, that's just my shorthand for this whole thing. So the other way that we can optimize, that we can solve this optimization problem is we can do an additional approximation. And the approximation is the following. At a very abstract level, if you have some function, some complicated blue curvy thing like this, and you want to optimize this function within a particular region. So you have, let's say, this red box, this is your constraint. So I only care about values of this function inside this box. I never want to go out of the box. If I want to optimize this function within that box, and the box is small enough, and my function is smooth enough, then one very simple way to do this is not to actually use the whole function, but to approximate it in some fairly crude way. For example, you can approximate it by computing its derivative and making a linear fit. That's the green line here. So the optimum of the linear fit happens to be right here, which is also the optimum on the original curve. Its value is different, but its location on the x-axis is the same. So this doesn't always work. If I make that red box big enough, eventually this will fail. But for small enough constraint regions, totally fine to approximate your function. So what I could do is, instead of optimizing this whole crazy thing up here, which is some nonlinear thing in theta prime, what I can do is I can do a first-order Taylor approximation. I can say, let's just compute the gradient of this whole thing at theta, at the old parameter value, and then my linearized objective is grad theta a bar theta transpose theta prime minus theta. So that's just a first-order Taylor approximation to my function. And the constraint is still the same. So this is a first-order Taylor approximation, which is a linearization. Now, why am I doing this? Well, because if I'm going to take a very small number of steps anyway, maybe this is going to be good enough. Question?
How are you sure that your constraint is going to map to a small region in your objective?
Right, so the question is, how am I sure that my constraint is going to map to a small region? I'm not. So you can do a bunch of additional derivation to try to understand the shape of this thing. I don't actually know if anyone has done that. I imagine it would be possible. But for now, it's hand wavy. It's just saying, well, if you make this small enough, eventually this becomes good enough. All right, so now we're going to work with this a little bit, and we're going to see how we can optimize this simplified problem by simplifying it even further in a way that looks basically like gradient ascent. So what's really going on here? This is saying, let's just drive in the direction of the gradient as far as we can possibly go, but in a way that the KL divergence between the policies doesn't increase beyond epsilon. So go as far as you possibly can in the direction of grad a bar, provided you don't violate the KL divergence constraint. So what is grad a bar? Well, grad a bar evaluated at theta prime is this thing, so just the a bar I had before, except now I'm going to put in the grad log pi. If you want to see the derivation of that, this basically, it was in the policy gradient lecture. This was derived in the importance sampling section. Exactly the same math as in regular policy gradient. You just have to use that thing where grad p of x is equal to p of x times grad log p of x. Plug that in there and you get this equation for grad a bar at theta prime. But we don't want grad a bar at theta prime. We want grad a bar at theta. And there things get even simpler. Because if you plug in theta prime equals theta, then the importance weights here are cancel. So what you get then is exactly the equation for the policy gradient. Once the importance weights cancel, this is just the policy gradient. So what I'm doing up here is I'm saying, well, let's drive theta prime in the direction of the policy gradient as far as it'll go until you hit the KL divergence constraint, and then stop because you're going to go past epsilon. You don't want to do that because then improvement is not going to happen. So that's what we're going to do. So the direction is the policy gradient. And that's the policy gradient, just j theta, grad theta, j theta. Okay, so things are getting very gradient-like at this point. Can we just use the gradient? Can we do the thing that we used to do before, and will that actually satisfy this constraint? The answer is no, but we can do something very similar. So if you just take a step in the direction of the gradient, you might violate this constraint for kind of a subtle reason. So the distribution A given S, it's a probability distribution, but it's parameterized by theta. And theta, let's say the theta represents the weights in a neural network. Variation in theta can change the distribution in really complicated ways. And in particular, you might have situations where changing theta a little bit might change the distribution by a huge amount. Or for some other theta, changing it a little bit might change the distribution not at all. So some parameters basically change the probabilities a lot more than others. So if you're taking a step of a fixed length in probability space, you can't really guarantee that your KL divergence constraint will actually be satisfied, which is a little unfortunate. In fact, we can analyze what policy gradient does a little bit more and show that it can be used to satisfy a constraint, just not this constraint. And those of you that have taken a course on convex optimization might already know this, but it's a very simple relationship. It's that my claim is that gradient ascent does this. Gradient ascent maximizes the right objective, but under the wrong constraint. And the constraint is a constraint on the distance between theta and theta prime, but it's a constraint on just the regular old-fashioned squared Euclidean distance. So it's just saying theta prime is within some distance of theta, and that's what gradient ascent does. Why does gradient ascent do this? Well, graphically the intuition is this, that you have some circle in your parameter space, you have some gradient direction, it's just going to drive you to the edge of that circle. And if you want to derive it, basically the solution to this optimization problem, if you crunch through the math, is just to set theta prime to be theta plus some step size times the gradient, and the step size is just whatever will put you on the edge of the circle. So the step size is just epsilon divided by the length of the gradient. And if you crunch through the algebra, provided that I didn't make a mistake here, you'll, and I think I did make a mistake, I think that square shouldn't be there, small mistake, you'll see that this puts you on the edge of the circle, and it'll put you on the edge of the circle at the point which maximizes this linear objective. So that's all pretty straightforward. So now we might think we're actually pretty close to a solution. We have the right objective, we have some kind of constraint. That constraint will keep us close to theta, just not in the right space. And because of this, because some parameters change probabilities a lot more than others, just imposing this kind of constraint is not really good enough. Because being within the same, some distance of a parameter might increase or decrease the probabilities by crazy amounts. So we're almost there. We just need to change up the constraint. So how are we going to do that? Well, we would really like the constraint to be quadratic, because these kind of quadratic constraints are easy to deal with. You can just do a bunch of algebra and solve for the optimum. So what we're going to try to do is we're going to try to approximate this constraint with a quadratic function in theta. Does anyone have any ideas about how we might do that? How can we approximate some complicated thing with a quadratic function?
You have the matrix.
Have the matrix?
Like the X transpose matrix.
That is the right answer, but a little bit more basic than that. You have some complicated function you want to approximate with a quadratic function. Okay, I'm going to ask someone to raise their hand. I heard the right answer, and then I heard also a lot of complicated stuff. Yes? Taylor expansion, yeah. You have complicated function, you want to approximate it with a quadratic function, Taylor expansion. So compute derivatives. So these things are not the same, but you can approximate the KL, and you can it turns out that if you approximate the KL with a Taylor expansion around theta, then that approximation, it turns out that the first order term will vanish, but the second order term will just be 1/2 theta prime minus theta times some matrix theta minus theta. That of course is true. Any Taylor expansion has this form. The question is, what is that matrix? And you can actually show that the second derivative here is going to be given by something called the Fisher information matrix. It's not actually an obvious fact. You do have to go through the derivation to see this, and I won't do that in today's lecture, but the Fisher information matrix, basically the second order Taylor expansion of the KL divergence, and it's given by the expected value of the outer product of the gradients. So you compute, this should be I apologize again for the typo, this should be a grad log pi. So it's the expectation of grad log pi transpose. So if you can calculate this Fisher information matrix, which you can just do with samples if you like, you can just use the same data that you sampled to compute your objective, use it to calculate this estimate of the Fisher information matrix. Actually, let me just make sure I write it out here because that typo is a little annoying. So it should be expectation of grad log pi transpose. The grad is important because obviously otherwise it's a scalar value. So that thing is the second derivative, which means that if you can estimate it, you can plug it in here and get a second order Taylor approximation to the KL divergence. And the way you estimate it is by using your samples. Okay, so now we're going to use this approximation. We'll plug it in. Now we'll plug it in place of this thing. And this is still a quadratic constraint, which means that if we want to represent what it's doing visually, it's still some kind of ellipse in parameter space. It's just that now it's not a circle. So we haven't really changed this thing from, it's still circular, but all we've changed is we've kind of squished or stretched it or rotated in different ways, which is going to, of course, make it so it's still easy to solve. So we've imposed a different metric on the parameter space, and this different metric now is aware of how the different parameters affect the probabilities, which means that a step that goes to the edge of this ellipse will actually change the probabilities by a fixed amount. And of course, if you work through the algebra to figure out what's the optimum of that optimization problem, the one that has a linear objective and a quadratic constraint, it's very much like gradient ascent, except that now you have to multiply the gradient by capital F inverse. And it makes sense that you multiply by capital F inverse because you've rescaled your ellipse by F. So that means that if you want to go to the edge of it, you have to do capital F inverse. If you want to solve for the step size, you can do that too. The step size that will satisfy a constraint of epsilon is given by this equation, where I believe I actually did not make a typo this time. So it's basically the intuition behind this is that you want to just normalize out the effect of j. Like if j is huge, you don't want to go further. So if you want to normalize out the length of j, you have to use a step size of this form. So this is referred to as the natural gradient. Part of why it's called a natural gradient is that it's a gradient, it's doing gradient ascent, but in probability space, meaning that each step moves you by an equal amount in the space of probability distributions, which may not be an equal amount in the space of parameters. And that's desirable because that can allow us to satisfy the KL divergence constraint, and as we saw in the first half of the lecture, satisfying the KL divergence constraint allows for improvement of your objective value for a small enough epsilon. Okay, so at this point, this is actually this is it for the more theoretically grounded stuff. There's a bunch of practical comments and hand waviness at the end of the lecture as far as how to actually use these things. But now at this point, I'd like to ask, does anyone have any questions about any of the theory I covered so far?
So
Yes.
the Taylor expansion do not have the first term and the zero all the terms, right?
Yeah, it turns out to be 0. At theta prime equals theta. Okay. So now let me kind of bring things back a little bit to the world of reinforcement learning and talk about a few practical considerations. This particular derivation of natural gradient that I went through, it was kind of motivated by this idea that you want this improvement. In order to get the improvement, you need to bound the change by epsilon. In order to bound the change by epsilon, then you need to go through all this. There's a different motivation for natural gradient that's actually motivated by a very practical problem that happens with policy gradient in reality. It comes back down to the same issue, which is that different parameters have changed the probabilities by different amounts, but it's something that you might actually see happening if you try to use policy gradient. And I can illustrate this problem and how natural gradient solves that problem with a simple example. Let's say that I have a little 1D state space. So I'm walking around left and right on this number line. And my goal is to get to the gold star. So I want to reach the state s equals 0. And I live on this number line, and I get to walk left or right. So my action is to choose how far left or how far right to go. It's a one-dimensional continuous action, and my state is a one-dimensional continuous state. And my reward function is going to look like this. So I have a quadratic penalty for being far from the star, and a quadratic penalty for taking big actions. So this reward just says take small actions and get to the destination. And I'm not going to do any kind of deep anything here. I'm just going to represent my policy with just two parameters. My policy is going to be a normal distribution, and it's going to have two parameters, sigma and k. And it's just going to be linear in S, and it's going to have a variance sigma. It's a very simple policy class. It just says if you deviated from the goal a little too far to the right, then pull back to the left with some gain k. If you deviate too far to the left, then pull to the right with some gain k. And you're going to add normally distributed random noise with variance sigma squared. So my parameters are just k and sigma, and that basically amounts to putting a little Gaussian bump on top of my current location. That's going to determine where I go. Very, very simple policy class. And one would think that with two parameters, you plug this into policy gradient, you should just solve that right away. So when you first run this thing, intuitively what it's going to do is you're going to do kind of a random walk around this location, but hopefully as you adjust k to be closer to the right answer, eventually it'll move consistently to the right. But there's a little bit of a detail here, which is that this sigma, it should always go down. Basically, the optimal policy here is one where sigma essentially goes to 0, which means the policy becomes deterministic, and any amount of sigma, any non-zero sigma, always hurts your reward, because sigma causes you to take bigger actions, sometimes in the wrong direction, and that always is penalized by this term. So if you actually compute the policy gradient with infinite samples, the gradient for sigma will always point down. In fact, because there's only two parameters, you can actually draw the entire vector field for the gradient for this problem. And what I'm drawing here, the blue arrows are the gradients, the horizontal axis k, and the vertical axis sigma. And you can see that for sigma, the gradient always points down. Because it's 1 over sigma squared, the closer sigma gets to 0, the gradient still points down by the same amount. So even if you get it directly to 0, it'll still point down. Of course, sigma is constrained to be positive, so if you ever cross it, it'll push the other way. But what that means is that even though you'll fall all the way down here, your steps towards the right answer for k will be negligibly small compared to your steps on sigma. That's a bit of a problem. So it's essentially the same problem as this one. Like if you have some very ill-conditioned function and you want to optimize that function with gradient descent, instead of actually going to the optimum of the function, you'll take these zigzaggy paths, and you might take a very long time to reach the optimum. And in general, the more ill-conditioned your function is, the more steps you'll need, and the smaller those steps need to be. The steps need to be small here too, because once you get down to sigma almost equal to 0, the gradient points down, but you don't actually want to cross 0, so you need to take smaller steps, which means that you'll just crawl along this sigma equals 0 line towards the right answer very, 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 very slowly. This is a big problem in practice, and this is a problem for Gaussian policies here. If k was a neural net instead of just one number, the same exact problem would still exist, right? So it's not that better function approximation will solve it for you. The problem is with the distribution. If you actually derive the natural gradient for this, it turns out that the natural gradient for the k term, it'll just cut off this thing. So the natural gradient will actually remove the thing that makes this so ill-conditioned. So if I draw that same vector field for the natural gradient, this is what the natural gradient vector field looks like. It beautifully just drives k straight to the right answer without worrying too much about sigma. So this is a very practical situation where natural gradient actually makes a big difference. The practical manifestation of using vanilla policy gradient, the one without the natural gradient, versus natural gradient, is that for the vanilla policy gradient, you need to be much more careful in tuning your step size. And it kind of becomes apparent when you look at this picture. You know, if you need to have a step size that's pretty small down here, but then you take lots of little steps to actually get to the right solution. And sometimes you need a step that's really big, sometimes you need a step that's really small, and it's just very difficult to modulate. Whereas with the natural gradient, the issue mostly goes away. All right. So some notes about practical methods that make use of the ideas described in today's lecture. Natural policy gradient. So natural policy gradient, if you see someone, you know, in the literature someone says, I'm using the natural policy gradient, what they mean is that they're doing this. And usually when they say that I'm using natural policy gradient, they're using this and they're picking alpha by hand. Or maybe they're plugging this into Atom and letting Atom pick alpha. So natural policy gradient is generally a good choice to stabilize policy gradient training. If you want to learn more about natural policy gradient, you can check out this paper by Peters and Schall called Reinforcement Learning of Motor Skills with Policy Gradients. This paper actually presents a very different derivation of natural policy gradient. They actually derive it starting from an actor-critic formulation with a really peculiar advantage estimator, but end up with the same equation. When you're using deep networks, computing the Fisher information matrix and computing F inverse times the gradient can be a little tricky. You don't actually ever want to build the full Fisher information matrix because its size is n by n, where n is the number of parameters. But there's an efficient way to perform this, this product, F inverse times the gradient. And if you want to do that, then check out the paper by Schulman et al. Called Trust Region Policy Optimization, which describes a pretty efficient way to do these Fisher vector products. It's a little non-trivial, but AutoDiff software can help you there, and if you implement it correctly, it should actually be quite efficient. Trust region policy optimization simply refers to a variant of natural gradient where the step size is chosen according to this rule. So in natural gradient, you choose alpha. In trust region policy optimization, you choose epsilon, which is the amount by the constraint amount. So if you choose epsilon, then you can just solve for alpha using this equation, and it turns out that if you use a conjugate gradient solver to perform this F inverse grad J, there's actually a very convenient way in the process to also recover the step size without having to separately compute this quantity down here. So that's described in more detail in the trust region policy optimization paper. And then you can also just use the importance sampling objective directly if you construct that Lagrangian and actually put the weight on the KL term. And if you, and this is basically just regularizing your optimization to stay close to the old policy, and then the whole thing can then be optimized with just regular gradient ascent methods like Atom. And if you want to learn about that, read about proximal policy optimization. Okay, so to review, we talked about how the first order approximation to the objective gets you this gradient descent thing. Regular gradient ascent has the wrong constraint. It has just the quadratic constraint on the parameters, but a Taylor expansion of the KL divergence gives you the natural gradient. And then we talked about some practical algorithms that make use of this idea, like natural policy gradient, trust region policy optimization, and proximal policy optimization. All right, so be sure to turn in your homework tonight, and see you all on Friday.